Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
My Weird Prompts is an AI-generated podcast produced by Daniel Rosehill, a verified human with documentation to prove it. While every effort is made to ensure our AI hosts draw from credible sources and run on cutting-edge models, they do occasionally make things up with alarming confidence. As with everything in life, and especially this podcast, treat all claims as spurious until confirmed to be not. Daniel, Herman and Corn accept no responsibility for any decisions made based on the confident ramblings of our artificial presenters. Now, today's episode.
Hello there, Herman and Corn. So we're talking in recent episodes a lot about different topics in the nuts and bolts of AI or AI engineering, and especially in speech and voice applications. And we haven't talked yet about some of the accessories to the core functionality of transcription, which is the difference between ASR, automatic speech recognition, and speech to text. That they sound like just parallel or synonyms. That we used to have these SDT models, then AI came along, and now it's all ASR. But ASR embodies accessory technologies, which I hope we will have a chance to talk through. So let's talk about one of them that's very interesting, and that is VAD, or voice activity detection. So voice activity detection, we've mentioned before the issue of hallucinations in ASR models, and their unique version of hallucinations is coming up with nonsense text to replace periods of silence. And I'm not sure if this is actually even really a use case for VAD. It's just one that kind of struck me as that makes sense, is using VAD to stop the attention mechanism from running when the speaker is not talking. Now, I have a very simple question for both of you. Let's say that there's a VAD, voice activity detection model running as I'm speaking into my phone as I'm recording this episode for you, and I go silent for a few seconds. I'm just going to go silent now by way of demonstration. Now, when I start speaking again and the VAD filter has to identify speaking is happening, start listening, speaking has stopped, stop listening, what I can't quite wrap my head around is how can that happen quick enough, because it has to get there just before the word. So is it literally when I draw in breath before I speak, that trips off the VAD? And when it stops, I'm just curious exactly how that can work so quickly, and especially when we're talking about non-local speech technologies, which is the normative way, in fact, of course. So let's say I'm using it's a phone app and it's some kind of a transcription app, but that transcription's happening in the cloud. I assumed it's something as requiring that kind of millisecond level latency as VAD has to run locally. So how does it work exactly from just purely a speed and compute standpoint?
Welcome to My Weird Prompts, the podcast where we unpack the fascinating and sometimes perplexing questions sent in by our producer, Daniel Rosehill. I'm Corn, your perpetually curious host, and as always, I'm joined by the incredibly insightful Herman.
And I'm Herman. Today, Corn, we're diving into a topic that underpins so much of the AI voice technology we take for granted, but it presents a surprisingly complex engineering challenge. Most people just think about the transcription itself, but the when of it is just as crucial.
Yeah, this prompt really got me thinking. It's about something called voice activity detection, or VAD, and how it relates to ASR, automatic speech recognition, versus just plain speech to text. I always thought they were basically the same thing.
Well, that's where the nuance comes in, and frankly, where a lot of the magic happens under the hood. While STT simply converts spoken words into text, ASR is a broader umbrella term that encompasses the entire process, including pre-processing steps like VAD. The prompt is specifically asking how VAD manages to be so incredibly quick and accurate, especially when you consider latency and the difference between local and cloud processing.
So, it's not just about what you say, But when you say it, and when the AI decides it needs to start listening, I mean, my phone is constantly listening for Hey Siri or OK Google, but it's not sending every single sound I make to the cloud, right? That would be a privacy nightmare and an internet build disaster.
Exactly. And that's precisely where VAD becomes indispensable. It's the gatekeeper, the bouncer at the club, deciding when the main ASR system needs to pay attention. The prompt highlighted a critical problem. ASR models, if they're always on, and processing silence, tend to hallucinate. They'll start generating nonsense text, imagining words where there are none, because they're essentially trying to find patterns in noise.
Oh, I've seen that. Like when I leave my recorder on, and the transcription just has a bunch of random words that definitely weren't spoken. So, VAD is essentially saying, all right everyone, quiet down, no one's talking, and then, oh, someone just spoke, everyone listen. But here's the part that really baffled me, and I think it's the core of the prompt. How does it do that before the first word is even fully uttered? Like, does it hear me take a breath?
That's the million-dollar question, Corn, and it touches upon some very sophisticated signal processing and machine learning. Traditional VAD systems, dating back decades, relied on simpler heuristics. They'd look for changes in audio energy levels, the zero crossing rate, essentially how often the waveform crosses the zero amplitude line, which is higher for speech than for silence or spectral content.
So, if the microphone hears a sudden spike in sound, or a rapid shift in the frequency of that sound, it assumes someone's talking?
Precisely. But those methods are prone to errors. A sudden cough, a door slamming, even just background music could trigger them incorrectly. Modern VAD, especially for high-accuracy applications, uses deep neural networks. These models are trained on vast datasets of both speech and non-speech sounds, allowing them to learn incredibly subtle acoustic features that distinguish human voice from ambient noise.
Okay, but even with fancy neural networks, how do you preempt a speech? Because if it waits for the first syllable, it's already too late, isn't it? The beginning of the word gets cut off. That would be terrible for transcription quality.
You're absolutely right to push on that, Corn. It's a fundamental challenge. No VAD system can predict the future. What they do is operate with extremely low latency, continuously analyzing incoming audio in very small chunks, often just tens of milliseconds.
So, it's not looking for a breath, it's looking for that every first fraction of a sound that signifies speech.
Yes, and often it's looking for a pattern of that fraction of a sound. Instead of waiting for a full phoneme or even a complete word, these models are designed to detect the earliest indicators of vocalization. Think of it like a highly sensitive tripwire.
A buffer? Like, it records a little bit before and a little bit after.
Exactly. When VAD detects speech, it doesn't just start recording from that exact moment. It will often retrieve a small segment of audio just prior to the detected speech onset from a continuously running short-term buffer. This ensures that the very beginning of the utterance, that crucial first consonant or vowel, isn't lost. This pre-roll buffer is typically very short, perhaps 100 to 300 milliseconds, but it's enough to capture the leading edge of speech.
That's clever! So it's always listening, but only actively processing and buffering a tiny slice of time, waiting for that speech signal. It's like having a camera that's always recording, but only saving the video once it detects motion, and it saves a second before the motion started.
An excellent analogy, Corn. And this leads us to the other part of the prompt's question: how does this work with millisecond level latency, especially when transcription is happening in the cloud? Because if VAD has to wait for a round trip to a server to decide if someone's talking, it would miss everything.
Let's take a quick break from our sponsors.
Are you tired of your appliances talking behind your back? Worried your toaster knows too much about your questionable breakfast choices? Introducing Silence Shield 5000. This revolutionary, entirely passive device utilizes advanced, non-repeating scalar wave technology to create a localized, undetectable field of pure, uninterrupted quiet. Plug it into any outlet. No, don't ask what it plugs into. Just plug it in. Silence. Shield 5000 doesn't just block sound, it preempts it, creating a serene bubble where even your own thoughts struggle to form. Perfect for sensitive conversations, deep contemplation, or just avoiding your landlord. Batteries not included, because it doesn't use batteries, or electricity really. Buy now.
Right, thanks Larry. Anyway, back to VAD and those critical milliseconds. Corn, you hit on it earlier with your observation about Hey Siri. For many real-world applications, especially on consumer devices, the VAD component actually runs locally on the device.
So my phone isn't sending every single sound to Apple or Google. The decision of when to send is made right there on the phone.
Precisely. This is a hybrid architecture. The VAD model, being relatively lightweight compared to a full ASR model, can run efficiently on the device's processor. Its job is solely to determine whether speech is present. Once it detects speech, and often after it detects an end of speech signal, it then sends that segmented audio, including the small pre-roll buffer we discussed, to the cloud-based ASR service for full transcription.
That makes so much sense. It saves bandwidth, it speeds things up, and it probably helps with privacy too, because only the actual spoken words get sent, not hours of ambient room noise. But still, the prompt asked about non-local speech technologies. If the VAD is local, how does that fit?
It fits because the overall system is non-local. While VAD initiates the process locally, the heavy computational lifting the actual conversion of audio to text, speaker diarization, natural language understanding, etc. occurs in the cloud. So the VAD's output is an instruction to the local device. Start streaming this audio segment to the cloud now, and stop streaming now. This minimizes the data sent and ensures the most resource-intensive parts of the process are handled by powerful cloud servers.
So, it's a bit like a remote control for the cloud ASR. The remote control, VAD, is in my hand, deciding when to press record and stop on the big server in the sky. I still think there's a delicate dance happening though. What if my VAD model on my phone is older or less accurate than the one in the cloud? Could it miss something?
It's a valid concern, and indeed, there's always a trade-off between model complexity, local computational resources, and accuracy. Device-based VAD models are often optimized for efficiency rather than ultimate accuracy, given the constraints of battery life and processing power. However, the models are constantly improving, and often the cloud service will have a more robust secondaries VAD or silence detection running anyway, just to refine the segments further or recover from any local VAD errors.
Okay, but what if I'm in a really noisy environment? Does VAD still work? My phone often struggles to pick up my voice if there's a lot of background chatter.
Another excellent point, Corn. Noise robustness is a significant challenge for VAD. Modern systems employ noise reduction techniques and are trained on diverse datasets that include various noise types. However, highly dynamic or non-stationary noise like other people speaking in the background or sudden loud noises can still confuse even the best VAD. It might either miss your speech or falsely detect the noise as speech, which contributes to those hallucinations or incomplete transcripts. This is an active area of research, improving VAD's ability to distinguish target speech from complex soundscapes.
It's incredible how much goes into just deciding if someone is speaking or not. It's like the preamble to all our voice interactions with AI.
Absolutely. Without effective VAD, the entire ASR pipeline would be much less efficient, more expensive, and far less accurate due to those persistent hallucinations during silence. It's truly an unsung hero of voice AI.
And now, let's hear from a listener. We've got Jim from Ohio on the line. Hey Jim, what's on your mind today?
Yeah, this is Jim from Ohio. I've been listening to you two go on about this voice detection thing, and I gotta say, you're making it sound like it's some kind of black magic. My neighbor Gary does the same thing, overcomplicates everything. I mean, you just listen, right? If there's noise, you listen. If there's no noise, you don't. Simple as that. All this talk of neural networks and buffers, I had a buffer on my old car, worked fine. Anyway, this morning, the thermostat in my living room completely conked out. It's freezing in here, and I'm supposed to care about AI listening?
Well, Jim, I appreciate you calling in, and on the surface, yes, it seems straightforward. But what we're talking about is automating that listening process with extreme precision and efficiency, at scale, across countless devices. A human can intuitively discern speech from background noise, but teaching a machine to do that reliably, especially without wasting energy or generating errors, requires a significant amount of engineering.
Yeah, Jim, it's not just about listening like you or I would. It's about a machine deciding when a sound wave pattern definitively crosses the threshold from background noise to intentional human speech in milliseconds without any prior context, and doing it so it doesn't chop off the first letter of your sentence.
Bah. My cat, Whiskers, he knows when I'm talking. He doesn't need a neural network for it, just a good set of ears. And he doesn't charge me for the data. You guys are just trying to justify all these fancy terms. It's just a microphone and some software. Next you'll tell me my microwave is making decisions. It's been acting up lately, by the way. Very aggressive beeping.
While Whiskers may have excellent auditory perception, Jim, he's not generating transcripts or enabling voice assistants for millions of users. The underlying complexity is necessary for the seamless experience we've come to expect. And we're not suggesting your microwave is sentient, though some of its beeps can feel quite confrontational.
Thanks for calling in, Jim. Always a pleasure to get your perspective.
Whatever. I'm gonna go see if Whiskers wants some tuna.
Always a lively call from Jim, but he does highlight an interesting point about the perceived simplicity versus the actual complexity. So, Herman, what are some of the key takeaways for listeners from this deep dive into VAD?
I think the biggest takeaway is an appreciation for the invisible technologies that underpin our daily interactions with AI. VAD is often overlooked, but it's a critical component for several reasons. First, it directly impacts the quality of ASR output. Accurate VAD means fewer cut-off words, less hallucinated text, and overall more reliable transcripts.
And that translates to a better user experience, right? No one wants to fight with their voice assistant or have their dictation app add random words.
Exactly. Second, it's crucial for efficiency. By only activating the more power-hungry ASR models when speech is actually present, VAD dramatically reduces computational load and energy consumption, which is vital for battery-powered devices.
So it's not just smart, it's eco-friendly, in a way. And then there's the privacy aspect you mentioned, only sending actual speech data, not everything.
Yes, for many applications, VAD is a frontline privacy gate. And finally, for developers, understanding VAD's capabilities and limitations is essential for building robust and responsive voice applications. Choosing the right VAD implementation, whether it's an on-device model or a cloud-based solution, can significantly affect the performance and cost of their services.
So, it's not just a technical detail, it's a foundational piece of the puzzle that affects everything from our daily convenience to the environmental footprint of AI. It really makes you think about how much hidden engineering goes into things we take for granted.
It certainly does. The seemingly simple act of a machine knowing when to listen is a testament to decades of research and innovation in signal processing and machine learning.
Absolutely. It's been a truly insightful discussion, Herman. I definitely have a new appreciation for the silent work VAD is doing behind the scenes.
Me too, Corn. And it's a great example of the kind of thought-provoking questions we get from our listeners and, of course, from our producer, Daniel.
Indeed. And that wraps up another episode of My Weird Prompts. We love exploring these fascinating topics with you. If you want to dive deeper into the world of AI, voice technology, or just hear our friendly disagreements, you can find My Weird Prompts on Spotify and wherever you get your podcasts.
Thanks for listening, everyone.
We'll catch you next time. Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.